A previous video on the practical application of Beer's law left off here with the specific application of a single wavelength absorption spectroscopy of a reacting mixture in a shock tube. I pointed out some of the main features of this setup, including the pitch and catch detectors, the decreasing concentration of fuel in the test section due to a reaction, and the single wavelength laser. I briefly mentioned some concepts such as beam steering and common mode rejection. Here I'd like to present a more detailed schematic of this setup and discuss all of the concepts that are relevant to its successful implementation. I'm also going to update some of my nomenclature from the last video. This table lists all of the considerations I could think of that need to be made for the successful implementation of a laser absorption spectroscopy setup applied to a shock tube. Each consideration is paired with a component or feature in the setup that is used to address that consideration. The purpose of this video is to discuss each of these considerations and components in detail. Some of the concepts may be more or less relevant if you are trying to apply this to something other than a shock tube. Remember that the ultimate goal of this setup is to determine the concentration of a specific species to as high of an accuracy as possible. So a lot of these involve filtering out signal variations that do not come from the changing species concentration. So let's start with those filtering components. Spatial filtering using a pinhole or iris allows only the most uniform portion of the beam through and is used to block the edges of a Gaussian beam, ghosting from spectral reflections, and light from non-coherent sources. Spectral filtering with optical filters eliminates any light that is not at the wavelength of interest. Common mode rejection can be thought of as a form of temporal filtering. Any variations in the laser power as a function of time will be eliminated by dividing the catch detector signal from the pitch detector signal. Dark mode rejection should eliminate ambient light noise and most electrical noise that is inherent to the detectors and the rest of the electrical setup. Beam steering is caused by large density gradients in the test gas, a shock wave in our case, and a focused beam is less vulnerable to beam steering. Beam divergence means that the beam diameter is expanding, and this can be stopped or reversed using focusing optics or parabolic mirrors. Detector saturation means every light intensity that is above the maximum signal rated for the detector will result in the same voltage output from the detector. So a high intensity beam may need to be reduced with a neutral density filter. Regardless of a laser's stated wavelength output, the wavelength may drift as a function of time, temperature, current, or damage, so periodic wavelength verification using a wave meter is recommended. Finally, an etalon is a component with two reflecting surfaces, which causes small interference between the light reflected off the front and back plates. Any glass optic with any thickness may produce unwanted etalon effects, including reflection of the light back into the laser and a self-mixing effect. This can be corrected for using anti-reflective coating, wedged windows, and even some slight intentional misalignment. So let's get started. This is the same setup I showed at the beginning of the video, but I've added some components and switched to a cross-sectional view of the test section so you can see the test gas inside of it. There are plenty of components here, and we're going to address them one by one. First, notice that I've changed my nomenclature to a more descriptive naming convention. The pitch detector simply outputs a reference signal, so I've renamed it the reference detector. The catch detector provides the signal we are interested in produced by the species of interest, so I've renamed it the signal detector. Everything in red is simply an abbreviation of the full name from the previous slide: neutral density filter, beam splitter, narrow band pass filter, off-axis parabolic mirror, and iris. In this depiction, the laser is off or not outputting a signal. When we turn the laser on, the shutter is closed, so it's blocking the beam. Here is when we would record the dark signals coming from both the reference and signal detectors. The dark signal is primarily composed of electrical noise, but it may include some signal ambient light. If the output of either detector had a constant bias on its voltage output, that would be captured with this measurement. None of this is from the laser or the sample absorbing it, so the dark signal will be subtracted from the sample intensities later on. There are a few important specs to consider when selecting a laser. These include the beam profile, whether that's Gaussian or top hat. We'll assume this one is Gaussian. Beam diameter and divergence. For example, this particular laser has a diameter of 6 millimeters, but there is some divergence angle, which means the spot size will be larger than 6 millimeters, say 1 meter away. Think of pointing a laser pointer at a wall and then pulling your arm back. The spot gets bigger the farther away from the laser it is. Beam intensity or laser power, and then of course laser wavelength based on what your sample is going to be, and then line width of that laser wavelength. Now let's open the shutter. I've eliminated it from the diagram because it's no longer in the beam path. Note the lighter edges of the line. I'm using this to indicate that Gaussian beam profile. If I looked at this laser head on, it would look something like this, where the intensity is greater in the center of the beam. And if you plotted this intensity as a function of position across the center of the beam, it would look something like this, a Gaussian profile. And by the way, when we direct the beam through this iris, the signal would look something like this, where only the most uniform portion of the beam is allowed to pass and those low intensity wings are eliminated. A set of lenses on either side of the pinhole may also be necessary. Look to this Thorlab spatial filtering tutorial to learn more. But enough with spatial filtering. The purpose of this diagram was to show how we achieve wavelength verification. Whatever species you are trying to identify in your sample is going to have a specific wavelength, say in microns or inverse centimeters, or a set of wavelengths of light that it absorbs at. Here we'd like to detect ethylene near 10.532 micrometers. 10.532 is approximately the center wavelength of this feature. The laser outputs a beam that is centered at 10.532 micrometers, shown with this black line. But the width of this line is 6 times 10 to the negative 8th micrometers. That's the spectral width of the laser beam. And the position of this line may drift by up to 1 times 10 to the negative 6th micrometers. But both the width and the drift of this line are so small, I can't even depict them on this plot. The portion of the absorption feature I'm interested in is approximately here, and the line width and drift of the laser are negligible compared to this width. And that's what you want. You want a laser beam with a spectral width and drift that are significantly smaller than the spectral width of the absorption feature. So we use these flip mirrors to direct the beam into the wave meter to verify that the laser is indeed outputting the stated wavelength of light. Then we flip the meters down and out of the laser path. With the flip meters down, they and the wave meter are out of the laser path. So I've taken them out of the diagram as well. Now the laser follows the path depicted. This is usually approximately what you'll see in an optical diagram. So let's follow the beam path through these different optical components and talk about their roles and relevant characteristics. The first component is the neutral density filter. The role of the NDF is to absorb some of the laser intensity to prevent damage to the detectors. If the laser output is greater than the maximum intensity rating of the detectors, an NDF will be required. You might notice that I lightened the shade of my line slightly after the NDF. This is to indicate that the laser power leaving the NDF is lower. You may also notice that the NDF is tilted very slightly. This is to prevent spectral reflections back into the laser. The NDF is supposed to transmit some percentage of the light and absorb the remainder, but there will always be some amount of light reflected as well. Tilting the NDF does offset the transmitted path of the laser slightly, but more importantly, it causes any reflected light going back towards the laser output to be deflected slightly so that it doesn't return back into the laser cavity. You also need to make sure that the NDF is appropriate for the wavelength of your laser. This is typically a function of coatings and window material, which is optical substrate or optical glass, and that will be true for all the optics. Once again, some good tutorials can be found on the Thorlabs website. The next component is an iris or pinhole which achieves some spatial filtering on the beam, as I already described. The next component is the beam splitter. I've depicted a plate beam splitter, but there are several other types available. Thorlabs has a beam splitter selection guide as a tab on all their beam splitter product pages. The plate beam splitter passes some percentage of the light approximately straight through, again with a slight offset on the transmitted beam due to refraction, and turns the remainder 90 degrees. Again, I lighten my line a bit to indicate that the high intensity incoming beam has been split into two lower intensity outgoing beams with about a 50-50 split between transmitted and reflected light. The reflected beam reflects off the front surface of the beam splitter, and the transmitted beam transmits through both the front and rear surfaces, but a small bit of the incident beam also reflects off the back surface, producing a third, much weaker beam called a ghost reflector. Note that I've depicted my beam splitter with a very slight wedge shape. Manufacturers often apply maybe a 30 arc-minute wedge, an anti-reflective coating, or both to the back surface of a beam splitter. The AR coating reduces the ghosting, and the wedge ensures that the ghost beam is not parallel to the reflected beam. The angle between the two is greatly exaggerated here. 30 arc-minutes is only a half degree. So you need to place the reference detector far enough away from the beam splitter to ensure that the ghost beam does not hit the detector surface. That provides the motivation for the next iris, which spatially filters the ghost beam and plenty of ambient light out of the reference signal. As long as we're here, let's talk about the path into the reference detector. Note that both detectors have a narrow bandpass filter on them. A bandpass filter rejects all light above some wavelength and all light below another wavelength, forming a band of wavelengths that can get through. You'd like your wavelength of interest to be somewhere in the middle of that pass band, and you want the band to be fairly narrow to eliminate as much non-laser signal as possible. Notice that there is no sample between the laser and the reference detector, so as the sample downstream changes, nothing changes in the reference detector. The only source of variation in this signal is the laser beam itself. The reference detector captures real-time laser variations that will also be sensed by the signal detector and is therefore used to later correct these variations out of the sample signal. This is called common mode rejection. Detector selection considerations include the detectable wavelength range, maximum signal and damage threshold, detectivity, the cooling method, amplification and filtering circuitry, the bandwidth or speed of the detector, and the active area. Now let's focus on the portion of the beam that was transmitted through the beam splitter. The next optical element it passes through is a plano-convex focusing lens. This is pretty specific to a shock tube. It helps reduce the effects of beam steering induced by the shock wave as it passes through the sample. Beam steering is a result of density gradients that cause a change in the refractive index, which will bend rays of light off their incident path, causing a momentary loss of signal in the signal detector as the gradient passes. We already saw a version of this in our upstream optics. A change in the refractive index from air to glass is the reason that the light is offset slightly as it passes through the NDF and beam splitter. A shock wave is essentially a very intense density gradient. Beam steering is most pronounced for large pressure gradients and non-homogeneous beam profiles, such as the Gaussian beam we're using here. Compressing the beam to a smaller diameter minimizes both of these effects. The plano-convex lens focuses the incoming light collimated beam. The beam waist should be at the center of the sample. So the lens should have a focal length that allows this placement. After the waist, the beam will begin to diverge again. Here, I accept a loss of some of the light due to this divergence and use the off-axis parabolic mirror to recollimate the light just before directing it into the signal detector. The windows installed in the tube have a few specifications worth considering. First, notice that I've made the windows, lenses, and beam splitter all the same color. This is to indicate that they are all made of the same type of glass. In this diagram, I'm assuming a single laser wavelength of 10.532 micrometers, which is infrared light. Zinc selenide transmits well from about 5 to 15 microns, so let's say all these orange optical elements are made from that. Most of the optical elements are also likely to be anti-reflection coated, specifically for the light in the wavelength range of interest. Because I am assuming a single wavelength laser output, the windows depicted here are flat. If I were using a tunable laser to scan a range of wavelengths, I would use a wedged windows with a shape somewhat similar to my beam splitter to reduce the likelihood of interference fringes from etalon effects. That's its own topic. Let's move on to this mirror. A mirror is simply used to change the path of the light, but why bother? I could just place the narrow bandpass filter and the signal detector directly after the second window and capture the beam without losing any of its intensity. So why bother turning it twice like this? This setup filters out non-coherent light. That is, light that is of the same wavelength as the laser, but not coming from the laser. The reaction in the shock tube will give off infrared light, some of which will come out of these windows along with the laser. The closer I place my detector to the window, the more combustion-induced scattered infrared light it might capture. I could just place the detector in front of the window a large distance away, but I'm limited by the geometry of my optical table. I can achieve the same path length by turning the beam a few times. Let's pause the discussion of individual components for a minute and consider the full setup as depicted. At the moment, there is no sample to absorb the laser. The shock tube is under vacuum, so the beam that reaches the signal detector is the initial laser intensity. This needs to be corrected for its dark signal and normalized by the reference signal corrected for its dark signal to get I0. If we record the outputs from both detectors on an oscilloscope, the voltages should be relatively constant, and the signal detector intensity will be at its maximum value. I should point out here that the output of the detectors and the line you see on the oscilloscope are not light intensities as my labels suggest. They're voltages. However, we never need to figure out what light intensity caused that voltage because ultimately two measurements with the same units are put into a fraction producing a unitless number. Whatever the conversion factor is from intensity to voltage, we can assume it's the same for both detectors, so it cancels out. Now let's fill the tube with sample. Note that the reference signal is unchanged, but the sample signal has dropped to its minimum value. Now the sample signal divided by the reference signal provides the transmitted intensity. Transmitted intensity will increase as the sample is consumed. So let's watch that happen. I'm going to play this a couple of times and point out a number of things that are happening simultaneously. The first time I play it, pay attention to the sample in the shock tube. You'll see a reaction take place that consumes the sample and emits some scattered infrared light. Here is a good point to describe the remaining parts functions. Notice that the reaction emits some scattered IR light that we don't want reaching our detector. The intensity of this light will vary based on the reaction, but it should be minor but not insignificant fraction of the laser intensity. It is diffuse light, so it spreads out and becomes weaker as it progresses along the laser path. The majority is then filtered out spatially at the iris. Only a small fraction of what remains at the narrow bandpass filter will be in the wavelength passband, so most of what reaches the filter will be rejected here. Now let's play that again and pay attention to the oscilloscope. As a sample is consumed, the transmitted light increases as evidenced by the increasing intensity at the signal detector. The reference detector remains unaffected, but note that if there was some anomaly or noise in the laser output, that would be captured both at the signal detector and at the reference detector and cancel out in the normalized transmitted intensity quantity. So now we can use Beer's law and our measured intensities to determine sample concentration X throughout the reaction. You should understand that this exact setup may not work for every application. For example, you might like to put the third iris directly in front of the signal detector. You might choose to recollimate the beam with a second lens at the exit of the shock tube, or use a flat mirror in place of the OAP. But now you should have a good idea of why you would make those types of decisions. I hope this video has helped you understand the practical considerations of setting up a laser absorption spectroscopy setup. If you know some things about laser absorption spectroscopy and you disagree with anything I've shown here, please say so in the comments. It will help me improve. Thanks for watching.